Hello everyone. In this video we will continue to examine topic 5.2, the heating effect of electric currents, and in particular we will unpack a multi-resistor circuit, in particular multiple resistors in series. So take a look at this circuit. This circuit gives an EMF and then the three resistances for three resistors in series. This is going to be a problem type you're not going to see often among the IB because, for one, it's a long problem. But in this problem type, what I'm going to ask you to do is basically solve out this circuit. What that means is find every possible value, every possible variable that you could be asked for. And to do so, you're going to want to do the following things in order. The first thing to do is to calculate the equivalent resistance of the three resistors. Then calculate the potential difference in current for every resistor. Then calculate the power generated in the battery and dissipated in each resistor. In doing so, you'll fill out a chart like this. And as you sort of learn this, I'd recommend making a chart like this for your different circuits. So for each resistor in the circuit, they get their own row, and then the entire circuit gets a row as well. And for each of those things, you'll have a resistance, a current, a potential difference across it, and a power through it. Now, we haven't dealt with power in multi-resistor circuits yet, but here's the key ingredient. To calculate the power generated or dissipated in a multi-resistor circuit, you're going to apply that set of power equations, right, the one that we saw for a simple circuit, for each individual element I. So, for example, if you're finding the power in resistor dissipated in resistor 3 and only resistor 3, then what you're going to care about for that power is the current through resistor 3, the potential difference across resistor 3, and the resistance of resistor 3. So for any particular part of the circuit, as long as you make sure that if you're using the variables, it's the current through that element, the potential difference across that element, or the resistance in that element, you can use our power equation here. So my recommendation would be to pause the video right now, make a little table just like this, and solve out this circuit. All right, so taking a look at this circuit, here's how we do it. The first thing is fill in everything we know. So we fill in the resistance of the different resistors, 2 ohms, 5 ohms, 3 ohms. We also know that the EMF is 20 volts, and so the potential difference across the full circuit, right, from here all the way through here, is 20 volts. So that's shown here. Then, step 1, find the equivalent resistance. Well, these are multiple resistors in series, so to find the equivalent resistance, we're going to add them up. 2 plus 5 plus 3 is 10 ohms. Okay, 10 ohms. So we fill that in here. Then we're going to find the current and the potential difference across each of the other elements. And the first thing we're going to do is say, okay, we've got 20 volts as our EMF. So we have the potential difference here, and we have the equivalent resistance here. But that's going to be 20 volts divided by 10 ohms is equal to 2 amps. So we can apply our definition of resistance of the whole circuit to get the current through the whole circuit. Now, this is a simple series circuit, and that means the current through each of these elements is identical to the current coming out of the battery and re-entering the battery. So that means if the current in the circuit, that is the current coming out of the battery, the total current, will be equal to the current through each of the different resistors. So we're going to go ahead and fill those in as 2 amps. Then we have each of the resistances and each of the currents, so we can find the potential difference across them by simply multiplying. Delta V is equal to I times R, and so 2 times 2 is 4, 5 times 2 is 10, 3 times 2 is 6. And we'll notice that 4 plus 10 plus 6 is 20 volts, just like it should be. To calculate the individual powers, there are a number of different ways to do it. But if you have this grid right here, my recommendation would just be to multiply I times delta V. That will usually be the easiest if you have the full grid already. So if the power is the current times the potential difference, then 2 times 4 is 8, 2 times 10 is 20, 2 times 6 is 12, and 2 times 20 is 40. So the total power generated in the battery and delivered to all of the resistors is 40 watts, but the total power delivered to resistor 1 is 8 watts, total power delivered to resistor 2 is 20 watts, and the total power delivered to resistor 3 is 12 watts. Notice that the power generated by the battery then is the sum of the power dissipated in each of the resistors.